Error correction in coding theory consists of all the developed strategies ensuring that two interlocutors, A and B, understand each other while communicating over a noisy channel. A well-known illustration of this principle is the radiotelephonic alphabet. Replacing each letter by the corresponding word in the alphabet allows human B to understand the message transmitted by human A even if the message is corrupted. With the language of coding theory, we say that the list of all words of the alphabet spelled in the radiotelephonic alphabet is the code. We can now question whether the ratio between the length of the words and the difference it allows to create between each word is a good ratio or not. More formally, we question the distance between each word of the code. Luckily, the notion of distance is a solid, well-studied notion in mathematics. In coding theory, there are two different frameworks and two different notions of distances that occupy most of the literature, the Hamming distance and the rank metric distance. We will now introduce them. First, consider the following framework. Two devices try to communicate together by sending sequences of bytes that you can picture as sequences of zeros and ones, but they communicate on a noisy channel that may flip none, one or many bytes. In other words, the transmitted message may have different ones turned into zeros and conversely. Now to measure error, we introduce the notion of Hamming distance between two words, which is defined to be the number of different bytes. For instance, the word 0000 and 1000 differ only on the first byte, thus the distance between the two words is exactly 1. You can also check that the distance between the word 1000 and 0110 is 3 because they differ on their first 3 bytes. Secondly, let us discuss matrices. Matrices are two-dimensional arrays or tabular that contain many entries. We say that a matrix is of rank 1 when all of its coefficients can be determined by a single non-zero column and a single non-zero row by multiplying together the entries on these columns and rows corresponding to the column and row of the entry you try to compute. For instance, if a rank 1 matrix has a coefficient 2 in its second row and 4 in its fourth column, then the coefficient at column 2 and row 4 is 8. All the coefficients can be computed that way. We can now assume that the two interlocutors A and B discuss by sending matrices to each other. After all, this is just a question of rearranging a line into a tabular. We will assume that the received matrix is the transmitted matrix plus one or more rank 1 matrices. We can then proceed by the same principle and state that the distance between two different matrices is 1 if they differ by a rank 1 matrix. We call this distance the rank distance. While the first notion of distance is used abundantly in various situations like file transfer or QR code reading, the second configuration may be viewed as a simplification of processes that may be globally reduced to a rank metric problem. For instance, if you consider a transfer of a matrix through several intermediaries that each apply a transformation to the word they receive before sending it to one or other intermediaries, then if an error occurs early in the process, then the error will hold and spread and severely modify the message obtained at the end. But if you construct your process so that the spread will create errors that can be measured with the notion of rank and if the message transmitted can be recovered with the rank metric, then you can correct a received message at the end of the line. Alternatively, you can imagine that your matrix represents a message partially stored of different servers, and study what happens if the servers burn in lines and columns. Now we can study the density of the codes. The distance between words of a code allows creating areas in the space containing all possible messages. The areas are constructed such that if the received messages lie in such an area, then the message originates for sure from the blue point in the zone. The zones must be disjoint, and we would like to construct a code that will make sure the zones together pack their whole space as we want the maximum possible amount of words in the code while being able to correct the same number of errors. If we refer to the Euclidean plane, such a packing is impossible because the areas created by the Euclidean distance around a point is a circle. We know that the best plane packing by circles is of density is pi divided by 3 times the square root of 2, and we cannot do better. With the Hamming distance, it is possible to get rid of this threshold enforced by the constant pi as one can create perfect codes, in other words codes of density 1. This is not the case for the rank metric distance, and it is proven that there exists no such perfect codes.